My presentation is divided in 5 parts. First, I'd like to give a short introduction why we should improve our crypto schemes. In the second part, I will describe the usually requirement for secure solutions, which is required also for the future, especially for post-quantum cryptography. The third chapter is directly about my concept for a lightweight public key encryption scheme. And the fourth part, I will give a short evaluation and comparison to other schemes. And in the end, I will discuss the scheme in relation to post-quantum cryptography and give a short summary. So what's the motivation for my work? More than 50% of all internet traffic uses RSA, which is very well known, so I won't explain it in detail. But the most people don't know that RSA is always or need to be combined with OAuth, so that the RSA is embedded in the communication stream. And this is usually used by every connection, which is HTTPS. So this is a lot of traffic, and it's very important, has a large impact. But this combination of RSA and OAEP has some weaknesses. The guy called Bleichenbacher showed this multiple times that this has some security issues, and RSA is only secure in the sense of well researched, but it is not secure in the sense of against adaptive chosen cipher attacks, in short CCA2. And also when we look in the future for quantum computer and with the Shor's algorithm, or we can probably make fast prime factorization, so RSA shouldn't be used anymore in the near future. So that's why we should focus on a post-quantum cryptography. And this has a relation with my presentation I will discuss later. First of all, to give an overview, when we talk about secure cryptography, we usually use the symmetric encryption with RS 265-bit as more or less standard for secure communication. And with quantum computer, if we have one, we just lose 1 bit, so it will be still secure. And we look in the asymmetric public key encryption world. Currently, we use RSA typically with 2084-bit, or when we have elliptic curves, then we need 512 bits. And with the time, we need to increase the keys, especially RSA, then the key size will increase very much. So we will have large keys. And this is not really practical, especially when we talk about IoT and Internet of Things, and we have not so powerful devices, so we need small keys. Also, the scaling from RSA increases very much, and when we look for elliptic curves, it scales linear from the key size, and the key is very small. So this is a mainly advantage for elliptic curves, small keys, linear scaling, and it's practical for IoT and smart cards, for example. And for elliptic curves, it's also a bit simpler to create more polymorphic schemes. I will go in more details later on what does it mean. So what's the usually scheme or the scenario what we look? It's very well known. We have a sender Alice, and Alice wants to send a secret message to Bob. Bob is our receiver. And for public cryptography, Bob first sends his public key to a key storage or a certificate portal. Then Alice needs to get this public key from Bob from the key storage, and then in the third step, Alice can create an encrypted message, send it to Bob, and then Bob can decrypt it with its private key. So this communication channel is secured with encryption, and also for the public key storage, only the public key is available. So the enemy, even if it is an crypto analyst Eve or a manipulation attacker Mallory, will be very difficult to access or manipulate the connection when we do it right. So, and how we should do it, I will show later. From this scenario, we get these requirements. As mentioned, we want to have tiny keys for fast transmission and also for storing. And when we talk about encryption, we want to have forward secrecy. So when we need to change key and these things, then only the transmissions in the future can be de-encrypted, not from the past. And also we want to have reusable keys for sure. What we also wish is an integrated message validating. It's not a must, but would be very helpful. Anyway, we also use encryption very often in combination with signatures or authentication. So when we can embed it or integrate it would be very nice. Otherwise, we have to rely or have to combine it with other schemes. The scheme should be very robust, so it's not malleability. So we can't, tweak it, or better would be to have proven security in the sense of adaptive attacks and CPA or CCA2. So this is more or less the highest possible security we currently know, and we need schemes which are provable for these attacks. And especially for the implementation, we have requirements and no data flow from secrets to area indices, or no data flow from secret to branch conditions when we implement it in software. Also no padding oracles, and we use in our devices central randomness, central random base. So every time we need it, then we can create a more or less secure source for random information or random keys. And we need to avoid unnecessary randomness with focus on audited or deterministic functions. So this is for implementation. And these requirements are also valid not only for my scheme, also for the future for post-quantum cryptography. When we have a look in related work, here I only focus in the presentation for post-quantum cryptography. For a complete historic view, please have a look in my paper. For the post-quantum cryptography, we have different approaches, multivariate polynomials, usually also can use hash functions, error correction codes, or lattice-based schemes. But we are focusing here on supersingular or elliptic curves. As I mentioned, it has advantages in the key size compared to all other approaches. And on the right side, you have grid matrix with the different security levels, split it in symmetric or constellation system and public key encryption schemes, asymmetric communication. And here you can see the scheme of RSA only provides the security for well-researched, whereas the scheme where I rely on is the Cramer Shoup scheme is cryptographic strong. This is the strongest condition we can get for public key encryption schemes. Informatic theoretical security is not possible, because when you have the public key, you always can do brute force and try to get the secret key. So this is the strongest security field we can get. Also, the post-quantum cryptographic scheme, which will be probably defined as standard, Kyber, falls also in this category. So here are some basics for public key, for elliptic curve cryptography. We create our cyclic group based on an elliptic curve. So when we have point P and we want to create a new point R, then we use elliptic curve for create a cyclic group. When we have point P and Q, we can calculate R. That's just simple calculation for interconnection of the interconnection points with the elliptic curve, and then just build the reverse. And this is defined as R as P plus Q. So we can calculate points on this curve just for short, basic revision of the basic. And we use this for the Cramer Shoup, or as a further development of the Cramer Shoup scheme to elliptic curves. Which brings us to my concept for a lightweight public key encryption scheme. Classically, I hope you all know Diffie-Hellman, RSA, and the Cramer Shoup are based on factories. And what we can see from the literature, it got further developed as the speed of the computer increases, and also we want to have smaller key sizes. These schemes are adapted from the classical field to elliptic curves. Same for Diffie-Hellman, RSA, and I now do this with this publication for the Cramer Shoup scheme. And for post-quantum cryptography, we also see the approaches which are not standardized or widely used yet. It has been done for Diffie-Hellman with SIDE or SIG. Currently for RSA, for me, I don't know if this exists. So far, I know it doesn't exist. And with this publication, I also focus on directly describes the approach to go further from elliptic curves to Isogeny elliptic curves. So in the end, or in the future, we will have also a scheme which will be post-quantum secure. Okay, for the basics, Cramer Shoup is very similar to RSA. I also call it 2 times RSA. It's nearly Cramer Shoup. I will describe later why it's in this way. Cramer Shoup is proven CCA2 secure, and but due to quantum computers and the possibility of with Shor's algorithm for factorization, we need a more secure base to make this scheme secure for the future. How does this scheme works? I have described it here with the mathematical function. I tried to do it hopefully in an easy way, not to bother you with too many mathematics. In red are the private key information, and in blue will be the public key information. First of all, we need 2 primes, P and Q. P can be calculated from Q, and these primes create the cyclic groups ZP and ZQ, and the one is a subgroup of the other. Furthermore, we need a public available hash function, which is collision resistant, classical one-way hash function, and our message, what we want to send, need to be in the public, need to be in the group G. If it not falls in it, we need to split it. Then we have multiple messages. Furthermore, we need some elliptic curves. Our scheme is not specific to one curve, so you can choose freely if you want to have the standardized step elliptic curve or the curve 25519, which is usually used for Hillmann encryption, and some random starting points. Usually these starting points are also standardized within the scheme. Here I use officially starting points from the other schemes. Okay. On the left side, you can see the classical scheme from Cramer Shoup, and on the right side, you see my transition to elliptic curves. Every calculation is within the cyclic group, so it's modular G, but I left it out for a better description here. So I just we are starting with random generation of factors, x1, x2, and so on, within the subgroup. And then we start calculating first C, which is point addition and point multiplication of x within the group G1 and G2. The same we do with the epsilon random values within the group G1 and G2. And we also need another point H, which is just a multiplication of random value Z within group G. And this already forms our public key with G1, G2, with the groups, and the points C, D, and H. Also the public available hash function. And the private key information will be the X's, the Y's, and the Z's. Very similar to Cramer Shoup. Okay, for the encryption, for the sender, here we just choose a random factor R. And then we start calculating the point U1 within the group G1 multiplied with R, and also U2 with the multiplication of R and with the point G2. And we do we encrypt our message M with the multiplication of the point H multiplied with R, and then we do point addition with our secret message M. So our message is in this point E. For the transmission, and this is special for Cramer Shoup, so we can prove later that the message is valid. We have our information U1, U2, and E modular with the function, and we get alpha. And for reverse calculation, we need to combine R with another calculation. So we have to calculate our point C with R and also our point D, R multiplied with alpha to get the point V. So our message for transmission to our receiver consists of U1, U2, E, and V. Very similar to Cramer Shoup. For the decryption, first of all, we check if the hash value shows that the message is unmodified received. We again calculate the hash value as the sender, U1, U2, E, and if it's we can verify it, then we know the message is valid. If not, then we should, we are not allowed to decrypt it. If it is valid, we can start our encryption. First of all, we need to negate our multiplication point of U1 and Z. So that is our private information. And then we can add with the transmitted value of E, and we get out of it M. It's easier to see in the classical scheme, I know. And that's why I always write down the classical scheme. Okay. Yeah. As a basic scheme of Cramer Shoup, is we can prove that it works for on the correctness. Also, we can make the proof for my scheme with elliptic curves. I have written down the proof in the paper, so if you want to have the details, please have a look in the paper. We also can prove that the scheme is secure in the chosen ciphertext 1 and 2 based on the Diffie-Hellman decision assumption. This means when you have the factors g power of A, g power of B, and g power of C, this is completely linear independent in the cyclic group for g multiplied A, g power of A, g power of B, and g the power of the multiplication A and B. So it's very difficult to cite which it is. And this is also, yeah, supported with the transmission of the hash values. And so the scheme is secure in these conditions. The main advantage of my scheme can be shown here. When you have a classical RSA implementation with a 4000-bit key, then you usually need for encryption about 120 milliseconds. For decryption, it's quite fast when you use the Chinese reminder theorem, but the key generation takes a long time, especially for large keys. Same security with elliptic curves. We have very small keys, but the encryption is much faster, also the initialization. The classical Cramer Shoup has with 200-bit security has in some larger key because it has multiple keys, but it's quite fast for calculation. And when we look in elliptic curve schemes for Diffie-Hellman, we will need large keys, or the new scheme of Kyber has very, very large keys for comparable security. It's very fast calculation for sure, but you need large keys. And this is a strong advantage of my scheme. We have small keys and the calculation time, it's quite acceptable, especially for when you have IoT devices or smart cards. So what should be mentioned in the discussion is when you have cryptographic schemes with 265-bit security, which is widely used, it is stated by NIST and also by the European Security ENISA. These schemes are secure at least the year 2030. Nevertheless, when we look for the development of quantum computers, we already know when you need to break elliptic curve with 256-bit, you need currently about more than 2000 qubits and more than 100 billion Toffoli gates. And when we look on the current development of quantum computers, the largest currently can provide about 400 qubits, but it's, yeah, so quantum computers still need a long time for development. Furthermore, this scheme I present is easily to enhance in the sense of a polymorphic scheme. You can easily change the elliptic curves you use for calculation. You also can use different starting points. And here I really like to mention the current scheme is probably not secure for post-quantum cryptography. That's why in the future we then need another step for supersingular isogeny elliptic curves. So this is what we do in the future. To sum up my presentation, I showed I adapted the cryptographic strong procedure of Cramer Shoup on the base of elliptic curves. It's a lightweight cryptographic scheme with small key sizes. Elliptic curves have a linear key scaling, which is very favorable in different scenarios, and it has a higher security level than RSA, which is very important for the future and for post-quantum cryptography. And with these tiny keys of the scheme, we have advantage for IoT. And what we will do in the future, we will adapt the scheme to supersingular isogenic elliptic curves, as mentioned, to have a post-quantum secure scheme. So thank you very much